explain what we do, how we do, why we do. Okay, so you know that when it comes to precision agriculture, the problem of the current remote sensing technologies are really ineffective in early detection and identification of pests and diseases. And growers needed to get very specific, reliable, and trustworthy, actionable data, meaning if you have a field and you have a problem in the field, you need to know what kind of disease you have, because if you want to spray, you need to have specific pesticide for every kind of pest. If you have weeds, for example, it's not enough to say you have weeds. You have to know whether these are 1 or 4 types of weeds before you can specify the pesticide that you need to apply to get rid of it. So we are providing patented innovative imagery acquisition method and patented high resolution yet affordable AI enabling sensors. I'll come to the AI enabling because this is the key, and software applications to provide actionable data for agriculture and forestry. Meaning we need to give the growers actionable data, meaning telling them, look, you have, for example, blight in this point in the field. What you need to do is go and spray according to what we found. Now, the sensors that we're using, we already got the international award at the Commercial UAV Expo from the press for our sensor. The sensors, as Maxim said, are of very high quality in terms of both dynamic range and resolution. We are talking about 5, 10, 14 narrow bands, resolutions between 10 to 7.5 for the 14 bands to 12 megapixel for 10 bands per band. Now, the cost of the product is not too high. It's less, in a way, it's more affordable, than the Altum, because some of the price was paid already by Sony, preparing, first of all, great cameras. That the basis of the camera actually was paid mostly by Sony. And we are developing our lenses with a big ODM, manufacturing them in big ODM in China. So the price, because of that, is not too high. This is what we got the prize for in the Commercial UAV Expo. Here you can see the 10 bands. As you can see, the bands do not look like bells, but rather like columns, which are very accurate. They are 30 nanometer wide. You have 10 bands. In the end, I'll show that we have some new surprise that includes something different, a bit different than the 10 bands like here. Here you have the specification of the bands. You can see the numbers here, 445, 570, 730. The numbers present each one. And you see that for the NIR, we're using 850, which is rather, if people know the graph, the way the vegetation works. So it's on the plateau after the 760, 65, it goes to like a plateau. Deep, this is deep NIR. Now, our patented sensor is different from all these sensors that you have in the market because of one simple reason. We enable taking multispectral data from a close distance. And this is the key issue, because taking multispectral data from high altitude is nice. It allows you to go for very small details and have effective early detection, spotting areas where things start. But the main thing is the ability to take close-ups from a close distance. And with our sensors, you'll see later when we take pictures from a distance of 3-5 meters, the resolution can be 0.5 millimeter per pixel, meaning it's in many ways even better than having an agronomist holding the leaf in his hand, because of the multispectral things features that we can see due to multispectral that the human eye cannot always see. Now, you cannot do this close inspection with all these sensors because they are multi-cameras. And by that, the distance between the different lenses for each band that you have in these sensors is too remote. And if you go too close, you get parallax. And if you have the highest resolution that you get is 3 megapixels per band, it's not like having 12 megapixels per band. So in any case, you go a longer distance, you have lower resolution, so it's ineffective in terms of AI, leaf level AI, what we call. Now, this is the TOPODRONE Quad, the 10 bands. In this case, I believe we'll be sharing these two presentations, right, Maxim? Will we be sharing it with the attendants of the seminar, of the webinar?
Yes, sure. We will share video recording, and we will share the presentation, and we will create a blog post on our website. So all information.
So I don't have to go into all the details, but the main thing is, as Maxim said, you know, that we are using high quality imagery, meaning the effective with the lens, the focal depth is 25 millimeter, unlike, you know, something like 4 or 5 millimeters with all these toys that you saw in the page before. And we are using f6, which is constant, and the distortion of the lens is less than 1%, meaning you don't have to do any correction. You don't use artificial pixels, but you use only the accurate pixels that you get from the camera. The relative illumination is 68%. This is something we fix with our pre-processing software, and I'll show it to you later. And the weight is, in this case, you see that the total weight of the camera with the lens for 10 bands, 580 grams. Now, this is a sample of a picture that was taken from 100 meters. The resolution in this case, I think as far as I remember, with the 12 megapixels, it should be from 100 meters. It's about 1.25 centimeter per pixel. When we go with our 10 with the 4 bands solution on the 24 megapixels camera, the resolution is 1.5 centimeter per pixel. Now, these are the bands, 10 channels. You can see here all the numbers: 405, 430, 450, 550, you know, 560, 570. And we have, in terms of red, we have 4 flavors, meaning 650, 710, 685, and 840. This is crucial if you want to have very good leaf level analysis, detecting specific pests and diseases. This is the 14 bands. As you can see, the 14 bands are filled. The whole spectrum is filled with narrow bands. I won't go through all the numbers. It will be too tedious. This is a sample of the 14 bands. On the top left, you can see the 850. This is like a single channel, but there is also a green channel there, because what we do is we align all these bands digitally, automatically, using the green channel, the different flavors of green, in order to get accurate digital alignment. This means that you don't have to do any kind of hardware calibration periodically, like you have to do with the cameras, like Tetracam, that you have to go to the lab and from time to time to calibrate the cameras. Now, when the cameras are too remote from each other, when you have multi-cameras, you have to do the calibration, but the calibration is also very tricky, because the calibration is different according to the distance you have from the objects. In this case, because we have all the lenses in a single mount, I'll just go to some picture here where we see it, you know, how close they are. Just go back. You see here, the distance between the camera, the lenses here is 22 millimeters between the remote lenses, and 11 millimeters between the lenses which are on top of each other from the center. So it means that in order to align them, it's not like here where you have 4, 5, 6 centimeters. If we are looking at slant range, for example, it can be even more than that. So alignment of the pixels of the different quadrants of the picture here is very easy and done by our software automatically with very high accuracy. This is as I said, this is the sample of the 14 bands. And now let's go to the software, because the software is a key issue for you guys. Once you acquired the pictures, first of all, the acquisition is done just like the Sony Alpha. All the 14 bands or 10 bands are acquired in a single image, which are actually composed of 4 different images, but they are kept in one file. And once they are split into RGB, we get the different bands. You know, in this case, theoretically 12, practically 10, because the NIR contaminates the green and the blue with one quadrant, so we use only the blue, only the NIR. Now you see the software that you have here, palettes. The palettes can be customized by the user. By the way, the pre-processing software is delivered free with the sensors. You can set the range of the survey between -1 to 1. You can set the range that you want to have the survey. You can have a correction of relative illumination when you upload the picture, and also for radiometric calibration. And you can set palettes by yourself. You can customize the palettes, and you can add also metrics. As you can see here, we support, many metrics. There's nothing special about it because it's common knowledge, but you can add your own formulas into the pre-processing software. And in this case, you can see this is Ndvi. What else can I show you? These are combination, for example, for combination of, this is probably NBG, the combined of 3 or 4, channels. You can combine any combination of channels that you can set here. The combination of channels that you want to use, whether you want to use 3, 4, 5, whatever. Now you have a batch conversion where you can output from a subdirectory all these metrics, all these analysis into a subdirectory. In order to do radiometric calibration, we are using a target of, the target is the X-Rite Classic board. It costs about something like $90. You can buy it in the BH Photos. The main advantage of this board is that the calibration is not affected by the angle of the light, and the calibration is unified for each of these 24 squares. We are using them for radiometric calibration to get the right radiometric calibration. You can use it at the beginning of the flight. Right now, we are working with a German company called Ndvi Europe on a light sensor of, it will be probably of 6 or 10 beds. I don't think they've decided it. It will be released by the end of the year. Now, once you process the pre-processing with our software, you can output it to a way that you can work with Agisoft Metashape or with the Pix4D fields, or the mapper, or any kind of processing software that you are used to be working with. If you have your own software application and you want to integrate it, they will be assisting you in combining the pre-processing, because we can supply some of it in source code in a way that you can integrate it with your software. Now, understanding, I don't know how many of you understand exactly how Ndvi works, but so let me give it in a very, very sort of high altitude, description. We are checking reflectance from leaves in order to know their position, their status. And when you have a healthy leaf, you get the NIR reflected and the red is being absorbed by the leaf. Now, the leaf is not so, it's not really healthy, it's a bit sick. The reflectance, the reflected light is minimized and the absorption is higher. So when you look at the reflectance is higher. Now, when you look at the dead leaf, you see that they are actually reflecting RGB and NIR more or less the same in an even level. So when you do all the agricultural metrics you saw before, you can find where leaves are really healthy or unhealthy. And now the tricky thing, in order to be able to do real analysis and come to real results, meaning leaf level, you need to go to high altitude, which is very high resolution, and it takes huge amounts of data. So and there's no way to know where a disease may spread in the field. It can happen from any point in the field. So sampling a field is something which is not wise to do, because it's like gambling. So you need to scan the whole field. And then if you scan the whole field, you do it from high altitude, then you don't have enough details. So you are actually guessing. But if you do it from low altitude, you may end up with too much data. So let's look at the numbers. This is just a sample. If you do 100 hectares at 1.7 centimeter per pixel, you may end up with 20 gigabytes. This is high quality JPEG. With RAW, it will be even far higher. If you do the very same 100 hectares at 1 millimeter per pixel, you may end up with 2.5 terabytes, meaning this is something there is no way you can digest. Too much data. So how do we solve this? This is our imagery acquisition patent, was cleared all over the world. You have altitude drone scanning the entire field without skipping any point. Then you do Ndvi. With the Ndvi here, you can see that there are 3 points that are lighter. Then we put them on spot them according to GPS, set a drone for low altitude. The picture you see here was taken with a drone in the UK from 3 meters. Once we process the multispectral data, you can see the multispectral signature of the disease. And this is something, this is leaf level examination, something that usually you cannot get an agronomist to do, because if the agronomist had to go through all the field to find just a few leaves like this is impossible. From the air, you could spot this point, send a drone and take the pictures. Now, this is the real case. On the left side, you see the RGB picture, and you can see that the blight and the color of the ground is almost identical. So if you try to do RGB classification, looking for the blight, in this case, you may end up with many false negatives, meaning many blight that will be identified as no blight but the ground, and could be also false positives, where you could find some rocks on the ground and identify them as a disease. But when you go to the right side and you look at the multispectral signatures, you see that the blight is completely separated from anything else. You don't get false negatives, you don't get false positives, you hardly miss anything. Of course, there could be leaves that are hiding behind other leaves, but most of it is very clear and gives you what we call actionable data, in the sense that you can tell the grower, this is what you have in the field. And if you attach to this also, the close-up of the RGB image, this is very easy for the grower to understand what he has. This is a sample that was done by a company called Geo in Brazil with the University of Sao Paulo, showing the levels of HLB, this is the greening disease, in the leaf, checked from a close distance with our sensor. And you can see the leaves that are set according to the level of HLB. On the bottom side, you can see how the multispectral data show it in a way that is very distinctive. Now, in this case, you could say, well, it's already visible, with the leaves. But when you go here, you see that the 2 leaves, on the left, on the top left, and the 2 leaves on the top right look very similar to each other. But when you look at them with a multispectral signature, you see that the 2 leaves on the left are quite healthy, but the 2 leaves on the right, on the bottom right, are infected with HLB. This is something that today you have to send the leaves to the lab to find them. And what Geo and UNES claimed that they checked 32 different samples like this with lab results and found 100% correlation between the multispectral signature and what they found in the lab. This is another sample that came from a company called Citri, one of our biggest customers. They were using the multispectral for counting oranges. They gave the color orange, but the original color was, at this stage, was still green, in order to enable predicting the yield of what you have on the oranges. This case, again, is something that was done with Geo UNES. This is capturing weeds detection in sugarcane. You can see very clearly that the yellow, the weeds are in yellow color. This is another sample that of almond orchard. And you can see that with different kinds of, I'll go now through to these 2 other metrics. You see that with every metrics of the same field, of the same orchard, you get different data, different results, and you may see where, like dark green trees are very healthy, where the ones that are colored in orange are not that healthy, although if you look at them like this, you don't necessarily see this. And I've gone through, these are different metrics, different agricultural metrics. Each one of them shows something in a different way. This is the typical NASA NDVI, which is not very accurate and not very detailed. So this is a sample, as you can see, of the same orchard, giving you different kinds of data regarding the health. Now we have a website, multispectral.ai, where you can see samples that we did just with 4 bands, showing multispectral signatures of different potatoes and some wheats and some other stuff. In this case, this is alternaria. That's another potato disease, where you can see the alternaria on the left side of the leaves. On the right side, you can see with the multispectral signature. We have many samples like this. And this is the last surprise. You know, we are with the camera, with the quad camera with 10 bands, we already will be shipping at the end of the year also 9 bands plus wide RGB, meaning what you see here on the bottom right is wide RGB. It means you'll be able to conduct at the same time multispectral and visual mapping at the same time, while the resolution is identical. And if you wanted to match them, it will be very simple. Today, the way we have it, it's like 7 bands plus RGB. We need to change one filter in order to move it from 850 to 765, and then we'll be able to supply 9 bands plus wide RGB. That's it. If there are any questions, I'll be happy to reply. I see that there is something in the chat. Calibration needs, yes. There is the calibration.
Maxim, please turn on your microphone.
Ira, could you read the questions? Because
yes, I read the question. Hi.
Okay.
The question is, first of all, well, anonymous attendee said that presentation was awesome. Thank you. Always nice to get compliments, you know. But hi, Puri Putra asks, hi, is there any calibration needed for AGROWING multispectral sensor? No calibration panel? No, you need a calibration panel to do the calibration. There is no way to do calibration without a calibration panel. You just take one single picture before the flight on the ground, and then you fly it. You can take another picture once you ended it. If the flight is just, you know, 15, 20 minutes, usually the changes are not that big during the flight. And the changes of, since we do it for multispectral with the same exposure time, and the ISO just changes. Usually the ISO change of the Sony sensor is doing a great job in keeping everything more or less at the same lighting, so you don't really have to do any correction during the flight. But it's always nice, you know, to have some, first of all, to take the first picture, and after the flight, take another one. In the future, we'll have also the option of integrating it with an ambient light sensor from EB Europe. Do you need to do any camera for light source? What another one? Just a moment. What is the ground that switched camera from 61 to 100 meter? From 100 meter, the resolution with 12 megapixels is 1.25 centimeters per pixel. This is more or less, you know, it's almost 4 times the Altum. The Altum is 4 centimeters per pixel. The flight plan is done within the TGI application. This is not for me, this is for you, Maxim, but I believe.
Yeah, of course. As soon as all our cameras integrated with DJI Pilot application or UGCS, you can use both of this application to make a mission planning, to fly with the terrain following mode, or even to fly in RTK mode. And of course, it's a great advantage. Then you just need to simply remove the lens to install a multispectral lens. And what you need to change settings inside of mission planning application because of the resolution, because of the parameters of the matrix. So you need to create 2 different settings for RGB camera and for multispectral. Yeah, it's possible.
I wrote my email address in the chat. So anybody that wants to get sample data sets to understand how it's done, to get better idea, don't hesitate. write me, and I'll see that Ilya will, our VP R&D, Ilya Makharov, will reply and supply you with data sets so you can witness it, from first-hand understanding what kind of quality you can get. There's another question here. This is from Frank Becker asking, hi, great presentation, which minimum shutter speed you prefer? Of course, it depends on light conditions, but you usually don't see people using less than 1 of 1,000. And in many cases, this is 1 of 1,600. It depends, of course, on the light conditions.
And of course, the speed of the flight. And of course, of the speed of the flight.
Yeah, if you fly, if you fly with 100 meters, it doesn't really, the speed of the flight doesn't really affect so much. If you do it with 1 of 1,000 or 1 of 1,600, we did some surveys in Inner Mongolia in the past under rain. It was cloudy, and we did it with 1 of 800 of a second, and it was we got very, very good results with it. Any other question? But as I said, you can write me, and we'll see to share with you data sets or any other information, specific information.
Okay, another one question. What is the GSD that reached the camera from 61 megapixel to 100 meters? So I think I don't understand, does it belongs to 61 megapixel camera or multispectral megapixel camera? If we are talking about 61 megapixel camera, RGB camera, you will get a resolution less than 1 centimeter. So it will be 6 millimeters or something like that.
It depends on the lens, because, if you are losing, for example, if you will be using with a 61 megapixels camera, a 50 millimeters lens, you will probably get, something that will be below something like 2 or 3 millimeters per
Exactly. But in general, if we install 24 megapixel, 24 millimeter lens, you will get a resolution less than 1 centimeter, definitely. So this is the idea. But if you need to install 18 or 16 millimeter lens as well, you will get very good results, but you will increase the coverage of the photos because of the wide field of view. It's very important for survey mapping as well.
As I said, since our the quad lens has, I think, I don't remember, actually it's 21.6 or 25 millimeters focal depth. It's in 12 megapixels. It gives you about from 100 meters, 125 centimeter per pixel.
Yeah. So if we don't have any questions, I would suggest that you can contact via our website or via website of AGROWING. You can send us a lot of questions, and we will answer all of your questions. We will provide you quotation and so on, and as well as this demo data sets with multispectral data, RGB data from different altitude.